in the previous video, we are discussing about the principal axis. We have said that the axis are said to be principal axis if the corresponding inertial matrix is a diagonal matrix. That is, all the elements which are not diagonal, they must be zero. That is, it's of the form. So a way to get a diagonal matrix is by using the eigenvalue problem. In the eigenvalue problem, what we do is we will equate this angular momentum is equal into an angular velocity into some inertial matrix which we get from a principal axis. So we can get it to the left hand side. We get Ixx minus I minus Ixy minus Ixy and Iyy minus I minus Iyz minus Ix minus Ixy Izz minus I into Wx into W by Wz is equal to 0, 0. Now the value of the I which we get from this expression, this will give us the value of a transverse principal axis with moment of inertia I corresponding to the x, y and z axis. Now a special property for finding the matrix is that in this case the angular momentum is proportional to the angular velocities. That is, we get H is equal to Ix Wx Ik plus Iy Wy Jk plus Iz Wy Jk. Whereas this is not the case in the case of ordinary axis. So now another property which we get for the moment of inertia matrix is if we want to rotate the 3D body in the 3D plane. Like suppose this is our 3D body, these are our I cap, J cap and K cap. Let's say we will rotate the body such that now our new rotation will be like this, in which this is our I dash, this is my J dash and this is my K cap dash. Now if we want to write the new moment of inertia, if we want to write the angular momentum along this and this axis, the new moment of inertia matrix will be given by into our previous inertial matrix. That will give us the new moment of inertia matrix. So let us take an example. Let us assume that we have rotated the body about the z-axis. Then we will get the new matrix, that is I dash, which is equal to I dash, which is equal to cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 into our series. That will give us the new moment of inertia matrix in this case. So that's all what we should have to understand about moment of inertia matrix. Now let's move to the last topic, that is rocket dynamics. By using Hamiltonian and Lagrange. So for this, what we have done is, let us assume a rocket which is going with a velocity v, and the gas has been coming out from it with a velocity c relative to this rocket. Now, if we were talking about inertial frame of reference, the velocity of this gas will be v plus v dash, which is equal to v plus c. Now, for simplicity, we can assume that the potential energy of this system should be 0. That is equal to 0. So now, finding the kinetic energy of this, we get kinetic energy is equal to kinetic energy due to this and kinetic energy due to this, which is equal to half into m. Let us assume its mass is m, and the mass of the gas is m into v square plus half into dm into v. Now, on expanding this, we get m v square by 2 plus dm v square by 2 plus dm v square by 2 plus dm into c into v, as which we can write as half into m plus dm into v square plus dm into c square divided by 2 plus dm into c into v. Now, since when dm is very small compared to 1, we can neglect it. The kinetic energy will be half m v square plus dm c square by 2 plus dm c into v. Now, L, which is our Lagrangian, is equal to k minus u, which is equal to k in this case. Taking dou L by dou v, which is equal to mv plus dm into c, and dou L by dou h, which is where h is the height, and we can write v is equal to h dash, assuming that the rocket is moving in a direction vertically in the upward direction, and assuming that the drag force which is applied on this rocket to be 0. So we can get this is equal to 0. Now putting